lecture. Okay. Well, at the end of yesterday's lecture, we just got through everything that's known about the Standard Model. So any questions that you have, now would be the right time to ask them. Oh, yeah, that's a good question. So, so what are they? There's G sub s. Let's write alpha s, alpha w, and alpha or alpha prime. So there are the three couplings, G sub s, G, and G prime, and I can trade them for these three parameters. Then, actually, there aren't any more parameters except for those in the Higgs sector. So the Higgs matrices, these Yukawa coupling matrices, are 3 by 3 complex matrices. So they're 9 parameters, 18 parameters each, and there are 3 of them. But in principle, we can rotate away most of those parameters doing these changes of variables. So an underlying theory might have, so now the Yukawa couplings. So these are 18 times 3 parameters. But within the Standard Model itself, you can only observe a limited set of those. You can only observe the masses. And then there are 4 CKM angles. Actually, 3 angles in a phase, we should say. And the masses, 6 quarks and 6 leptons, there are 12. So of these 18 times 3, 54 parameters, only 16 are actually observable with Standard Model processes. Yes?
Why are they called Yukawa couplings? Because it's a coupling to a scalar field?
Anything of the form F bar gamma F times the scalar field is called the Yukawa. Okay, so if I count the parameters this way, there would be 3 plus 12 is 15 plus 4 is 19. And there's one more parameter, which I'm about to introduce, which is the what we could take to be the Higgs mass. So that's the 20th parameter. So that's not too many, given that this describes everything in particle physics. Okay, it's certainly you'd like to understand where these parameters come from. And some of these parameters are not known so accurately. But I think, actually, except for the Higgs mass, they're all known to at least 10% accuracy. And these guys here, I've told you, are known to 3 significant figures. And also the top quark mass is known to 3 significant figures. Alpha S is known to almost 3 significant figures. Maybe 2. No, sorry, that's wrong. Maybe 2% accuracy. So everything fits together within that very kind of well-defined space that's allowed by the experiments. So, yeah, pretty good model. Yes?
Can you write the equation for the vacuum expectation of the Higgs field, just like, angle brackets,
Yes.
Higgs field, in V over root 2, or whatever it is?
Right.
Does that come from somewhere? Can you calculate that, or is that input?
I
mean, that's where the potential's minimized, right? But
that's where the potential's minimized.
so you just say that's...
So to the extent that you believe that the potential is real, then the potential would explain that. Now what explains the potential? I don't
Right.
know.
But can you do a calculation to see that? Like, I mean, if
What do
you
you-
just tried to take the expectation value, is that what you get?
Sorry?
Can you just take the expectation value of the Higgs field and find that number, or it's still input?
No, I don't understand what you mean.
Okay, so you have...
I mean, let me write this equation on the blackboard because it's actually the first equation in today's lecture. Minus mu squared phi squared plus lambda phi to the fourth. So I can just write down this potential. And that potential has a shape that looks like this. And it has a minimum. And the minimum occurs at V, which is given by mu squared over lambda to the 1/2. And some factors of 2. I think with all the... So if you say that the minimum occurs at a value V over the square root of 2, then V is equal to mu squared over lambda to the 1/2. So this is all totally unambiguous. Now, when you start doing quantum field theory, of course, this potential gets renormalized. And so then you need to work a little harder. You need to figure out what are the radiative corrections to this potential. You probably want to figure out what your experimental input parameters are so you can correctly renormalize this equation. The experimental input parameters aren't very obvious. Probably taking MW and the Higgs mass are two convenient ways to do it. And we'll talk a little about the problems of this potential in this lecture. But in principle, you can just carry this through order by order in perturbation theory. This expression, if I hold these things fixed, will get some perturbative corrections. As long as lambda is small, I can handle that with weak coupling perturbation theory. And the whole thing is under control. Okay. Of course, the big question is, why did I put a minus sign here?
Right.
And the only answer I can give is that experiment requires that you do that. You have to. There's no explanation for that within this model. Okay. Well, does that answer your question?
I'll do that later.
Okay. But given that this is the potential, that's the minimum.
Yeah.
And the minimum corresponds to a non-zero, that this field has to flop over and take a non-zero value everywhere in space. And there's nothing wrong with that.
Yeah.
Okay. I mean, as John Berlinski's been explaining to you, there are lots of statistical mechanical models with that property. So if it can happen in a block of stuff, it can happen in that. Yes?
The lambda has units, right?
Lambda is dimensionless.
What about mu?
Mu has the dimensions of mass.
Does that cause problems in the theory? In
Yes.
renormalization?
Yes.
How?
Well, A, if there's a mass scale, you should explain where that mass scale comes from. And B, if you have a term in the Lagrangian phi squared, which is allowed by all symmetries, then that term can get renormalized. And the renormalization corrections to that term are going to be quadratically divergent. So those are two problems. They're pretty hard problems. Yes?
So it's on the negative mu squared thing. Like we call it spontaneous symmetry breaking. But
Yes.
The m squared, like the symmetry breaking would be from going from positive m squared to negative m squared. But we can't, like nothing ever really changes in H like that. Like in the condensed matter system, there's usually a field you can apply that causes the symmetry breaking.
Right.
But here you just set the problem up so it's like that. So how is it symmetry breaking rather than just like you've made an asymmetric
Well,
thing?
what you mean by symmetry breaking is that the symmetric point is here. But that point is unstable. It's not the minimum of the, it's not the minimum energy of the Hamiltonian. The minimum energy of the Hamiltonian is an asymmetrical configuration. And in fact, as we've already discussed, there's a manifold of asymmetrical configurations. So that's what's actually called spontaneous symmetry breaking. You have a Hamiltonian, which has where you can define a symmetric state, but that symmetric state is not the minimum energy configuration of the Hamiltonian. There's another eigenstate of the Hamiltonian, which has a lower energy, but it doesn't preserve the symmetry of the Hamiltonian. That's what's called spontaneous symmetry breaking. Now, in statistical mechanics, you deal with materials, and when you have a material, you can change it. And so whenever you change the material, you then get a phase diagram. So, for example, you could use temperature. So it's known that if you heat up the standard model, if I now go to finite temperature actually changes this potential because thermal fluctuations basically create a potential which favors being at the symmetric point. So if you compute the temperature corrections to that potential, so basically diagrams like this, where in this loop you consider the thermally excited bosons, the real bosons that are thermally excited, you actually get a contribution here. And the potential that looked like that over here begins to look, well, it depends. It could either be less rounded here and then eventually go through zero like that, or sometimes it can even look like this. And so there's when this thing pokes up above zero, there's a first order transition. This is actually what happens in the standard model. What shall I say? So this is one parameter where if you change it, you can go from a minimum configuration which is asymmetrical to a configuration which is symmetrical. Maybe I should just say we're talking about temperature, so we're no longer talking about eigenstates of the Hamiltonian. We're talking about the configuration which has the lowest free energy. But in a magnet, you can consider, for example, just changing the element of which the magnet is made, or doping it with some other material. So you know that magnetism in nature occurs in some very restricted region of the periodic table around iron and cobalt. If you move a little to the left on the periodic table, magnetism goes away. And that you could model by changing some, essentially the filling of F levels. So there's some parameter that you could adjust in a model that would mock that up. Yeah.
And the minimum becomes the origin again.
Right.
Does that say anything about the mass of the particles?
The mass of?
So the Higgs mechanism gives mass to the W boson.
Absolutely.
So when you go through that phase transition, they lose that mass?
Absolutely. Now, there are other masses that occur at finite temperature. So, for example, W bosons at finite temperature interact with all these thermally excited photons. I mean, of course, there's all this thermally excited stuff. The quarks and leptons swimming around, the spaces of plasma, the photon and the W boson are plasma excitations in that. So you have to take that into account. But yeah, I mean, so let me draw another stage in this diagram. Let's say there were actually a first order phase transition. So at high temperature, this is effectively the free energy, and the preferred configuration is here. At low temperature, the preferred configuration is here. At some point, then, you begin to, you're here, you begin to notice that you're supercooled. And so you begin to start nucleating bubbles of this stuff within the vacuum. So the dynamics of those bubbles is quite interesting. It's been studied in some detail. You have a bubble with the expectation value of phi not equal to 0, which is moving outward because it's energetically favored into a vacuum where the expectation value of phi is equal to 0. And in here, you have, for example, massive W's and top quarks. And out here, you have massless top quarks, and the W is some plasma oscillation. And so, needless to say, when this bubble goes out and rips through space, it eats up all the top quarks and W's that it's going through, and it has to massify them. And that actually is a drag on the bubble. So the bubble doesn't expand at the speed of light as you would naturally think it would. It expands at about 1/10 the speed of light. And there's some theories of the generation of the baryon number of the universe that rely very heavily on the dynamics of these bubbles. So there's a whole line of investigation there that you could follow. Yes, please.
If this has any relevance in cosmology that you already.
Sorry?
I was going to ask if this has any relevance in cosmology that you already.
Yeah. This, presumably something like this actually happened in the early universe. And, then you can ask, well, did it do good or did it do bad? If it's a bad thing, we might want to have a fundamental equation that doesn't allow this. And if it's a good thing, like it generates the baryon number of the universe, we might want to have more of it. Maybe we don't have enough in the standard model. So there's a large discussion of this in cosmology. Yes?
What would exactly be the temperature? It's like confusing.
What would exactly be the
Yeah,
temperature?
temperature is like a statistical constant.
Yes.
If you are talking about like vacuum and particles,
Yeah.
it seems a bit odd to talk about temperature. Like
Why?
What is your reservoir
Why?
when you are talking about the entire universe?
How about the temperature of the cosmic black body radiation? Right? You point a telescope anywhere in space that there aren't stars, and you register a temperature of 2.77 degrees Kelvin. Right? In earlier histories of the universe, that temperature was a lot larger. That temperature has been decreasing like, 1 over T to the 4th for 1 over T cubed, rather, for some time. So there was definitely an era in cosmology when the just thermal particles in the universe. So the universe easily stays in thermal equilibrium, right? Because these particles are interacting through electromagnetic interactions. But the expansion of the universe is governed by gravity. So somehow the Planck mass has to come into it. And the formula for the expansion of the universe has the Planck mass in the denominator. So there's almost no formula you can write with the Planck mass in the denominator where the gravity isn't smaller than everything else. And so if you have a plasma of electrons and photons, they have plenty of time to come into local thermal equilibrium. Now, of course, it is a mystery why the universe over there has the same temperature as the universe over there, even though obviously they're not in causal relation. And so that's a very important problem in cosmology called the horizon problem. And that problem was solved by inflation. I mean, this is one of the fantastic, there are a lot of crazy things about inflation, but this is the fantastic thing about inflation. Inflation gives you a picture of the history of the universe where those very separated regions were once in thermal contact. And they had a chance to equilibrate their temperatures. And then once that initial condition was set, the temperatures are still equal, even though those regions are no longer in causal contact. And so from the theory of inflation, you get an answer to this problem. But if I look at any causally connected region in the universe, everything in there has plenty of time to come to thermal equilibrium. And so if I started out the universe at some temperature, or even if I started out a causally connected region in the universe with some energy, on the scale at which it's expanding, the scale at which the universe as a whole is evolving, it very quickly comes into thermal equilibrium and it stays there. And in fact, when you do cosmology, you can think of the expansion of the universe as adiabatic, and it conserves entropy. And the entropy conservation in cosmology is a very important principle. It allows you to do a lot of things. Yes?
The area outside of the expanding phase bubbles is still light lack. How does the phase bubble expand into it?
I'm sorry?
So the particles on the inside of the bubble are massive.
Yes.
and so presumably the bubble expands at some finite temperature below C, speed below C.
No. The bubble itself, I mean, that doesn't have to do with the particles. The bubble would be some kind of classical solution of the field theory. And that classical solution, if you work it out, the asymptotic behavior is that it actually accelerates to the speed of light. So the idea is that the bubble wall has some stuff in it. So if you go, for example, from here to here, you're looking at a solution where phi, let's see, so you're here in the middle. So phi starts out here in the middle. Sorry, I'm throwing phi this way. So this is V, right? And when you go outside, you're here. And typically what that looks like is that phi undergoes some excursion like that. Okay. And then because there's terms that involve the derivative of phi, this region here has some energy associated with it. And the evolution of that solution, if you just put it into the field equation and solve it, is that it evolves outward like that. Asymptotically, this wall reaches the speed of light, and it gets Lorentz contracted. It gets narrower and narrower. Now, what combats that is the fact that as the particle goes out, the medium that it's sweeping through is not empty. It contains all these massless W and bosons and top quarks. And so as it sweeps them up, it has to do something to them. And there's a quantum correction that slows the wall down. But in principle, there's no problem with a bubble wall expanding at the speed of light. If there were literally nothing outside it, it would eventually expand at the speed of light. Expanding at the speed of light is scary, right? Because if there was some vacuum bubble that just nucleated on Alpha Centauri and it started coming toward us, we wouldn't get any warning. Of course, if there were a vacuum bubble that nucleated on Alpha Centauri and it started coming toward us at 1/10 the speed of light, it would take a year to get here, and we'd be very worried during that year because there would be absolutely nothing that we could do about it. Yes?
It just happens that it's related to this V.
Yes?
As a rough guess.
That's right.
Back to your question.
That's right. So the order of magnitude is 100 GeV.
We'll see this in cosmology next week.
Ah,
We're
okay.
discussing it, I think.
Okay. Okay. Maybe this is more interesting than what I was going to tell you about. Anyone have any other questions? Yes?
If you could crank up the luminosity and the energy and say the LHC, could you get these massless states propagating through?
The problem is that with weakly coupled quarks and gluons, it's really hard to get a whole region of space excited to high temperature. So at the LHC, we mainly have individual quark-gluon reactions. And those couple really poorly to things that are coherent excitations of space that are over a large distance. And so it's just really hard. People in the 80s, people discussed the question of whether some classical solutions called sphalerons in the electroweak theory could be excited by quark-quark or quark-gluon collisions. And when people really computed the rates seriously, they turned out to be incredibly small. And they had factors in them like e to the minus 1 over alpha weak. So that's a very small number. Now, it is possible to do the analog of this in the strong interactions. You remember I told you the strong interactions have a spontaneous symmetry breaking of chiral symmetry. And so there is a way to get chiral symmetry restoration experimentally, which is you take a big nucleus, two big nuclei, and you collide them together at high energy. And they did these experiments at Brookhaven at the collider called RIC, And they've done some of these experiments at the LHC. And so at the LHC, they actually collided lead ions with each other at energies that correspond to about a TeV per nucleon. That's pretty impressive. So then what happens is the lead ions go through each other, and they leave behind a region of space which is extremely hot at a temperature of many GeV per Fermi. And then that region expands outward. And eventually, as it expands, it cools. And when it cools to 100 MeV, then it all turns into pions. And you get these dramatic events where thousands of pions come out. So by studying these events, you can study some properties of what's called the quark-gluon plasma. That is the thermally excited phase when you have high enough temperature to restore chiral symmetry. And you also create a plasma of massless quarks. And then you also kind of destroy quark confinement because there's so many quarks around that it doesn't matter whether they're confined. There's always some guy near you to balance the color. So at the LHC, they saw some amazing phenomena in this kind of collision. So there are events where what the event looks like is, well, first of all, thousands of particles come out. But that's not the interesting part. The interesting part is that over here there's a jet which has a PT of order 100 GeV. And on the other side there isn't anything. And the picture of this, which seems to make sense, is that you have this cylinder of plasma that you've made. And you have in this part of the cylinder, you have a hard quark-quark collision. And one of these quarks gets out, and it makes a 100 GeV jet. But the other quark has to burrow through all this plasma to get out. And in the process of burrowing through, it interacts strongly with the plasma, and eventually it loses all of its energy. And so that energy gets totally dissipated, and kind of just nothing particularly visible comes out the other side. So doing experiments like that, you can actually test the properties of the quark-gluon plasma. And well, there's a whole story to tell about that. It's quite interesting. Okay. So some of these thermal effects, as I say, really do exist, and there's experimental evidence for them. In the Higgs sector, we haven't gotten that far yet. And no one really knows how to get a whole region of space to the temperature that's above the symmetry breaking phase transition of the standard model. Okay, I'm sorry. I don't know how to do it either. Okay. Well, maybe I should give you this lecture. Okay. Okay. So, actually, I have these equations written up here on the blackboard. Let me write them up again. Okay. So, as we said in the beginning of this discussion, the standard model really relies on the spontaneous symmetry breaking of SU2 cross U1 symmetry. And the way that's done in the standard model is we postulate this Higgs boson field. So we postulate a field which is a complex doublet with isospin a half and hypercharge a half. And then that field has to be coupled to more or less everything in the standard model. And I've written those couplings down in the past couple days. And then I have to postulate some kind of potential for this field. So if I want a renormalizable Lagrangian, I would write down that if I only have one field, that's the most general thing I can write that's consistent with all of the symmetries of the model. And then I just take the coefficient of the parameter mu squared. I define that coefficient to be negative. And as I've already told you, where that comes from, I don't know. And I'll argue a little later that it's actually not possible to understand that within this model. But we take this coefficient to be negative. We get a potential of this form. We arrange that the minimum energy of the Hamiltonian is in an asymmetrical configuration. To leading order in perturbation theory, here's the expression. And then once we've got this V, then the whole standard model works. We get masses for the W and the Z. We get masses for all the quarks, all the leptons. Everything works. Even, I showed you yesterday, there are very subtle aspects of the decay of the top quark to the W boson that somehow rely on this Higgs mechanism for generating masses that work out correctly experimentally. So it's surely right. The only thing that's maybe not right is this particular expression, which is very mysterious and is, I should say, totally untested experimentally. So V, we know what the value of V is because there's a formula MW equals GV over 2, and we know what G is. So G is about 250 GeV. That gives us one combination of mu and lambda. And so we need one more observable parameter to kind of complete the parameter list of the standard model. One possible observable parameter is to compute the mass of, so I told you that of the field phi, we can always go to a gauge where phi takes that form, and we can gauge away all the other components of that field. So there's only one scalar field left, and when I quantize that one scalar field, I get one more particle, which is called the Higgs boson. And roughly, the Higgs boson is the quantum of oscillations in this well. If I plug this into here and just start expanding, what you get is mu squared h squared plus some nonlinear terms in h. And so from that, you can identify the mass of this Higgs field is 2 mu squared. And so what you can see then is that if I take the mass of this Higgs particle as my additional parameter, the standard model is now completely determined. I've determined every parameter if you give me what the mass of the Higgs boson is. And therefore, I can just predict all other properties of the model, including the properties of the Higgs boson. And so this is not totally satisfactory, because it would be nice if we had actually discovered that particle and could measure its properties. But we hope eventually that'll happen. And along the way, maybe it might be a good idea to see what the model predicts about the properties of that particle. It's actually an interesting story. And so let me just work out some details of it for you. One thing I should say is that the mass of the Higgs boson is the parameter mu. We can then get lambda by looking at the ratio of the mass and V. So if you just eliminate things, you can write lambda squared over 4 pi is equal to, so let's back up a little. Lambda is equal to 1/2 m Higgs squared over V squared, or lambda over 4 pi, which is the thing which would be an analog of alpha for lambda, is m h squared over 8 pi V squared. So the square root of 8 pi is something like 5. And so somewhere around a TeV then, this number here becomes of order 1. So for a mass of order TeV, this number becomes of order 1, and the Higgs sector becomes strongly coupled. So roughly then, there's a range of values that you could have for the Higgs mass. It could be extremely low if lambda is small. It could range all the way up to a TeV. There's some problems that, basically problems in the quantum theory. This theory, taken extremely literally and done at the quantum level, will begin to break down when m goes above about a TeV, or when lambda becomes very large. Roughly, the renormalization group equation for lambda has a pole at some point, and then you really get into trouble. And that occurs when the Higgs mass is, of course, it's a strong coupling. You don't really know where it is, but it's roughly 700 or 800 GeV. So the Higgs could be anywhere from, you might say first, 0 to 700 GeV in mass. Now, there's a little region around up to 10 GeV, which is actually excluded on theoretical grounds. When you compute this potential, the radiative corrections to the potential don't allow, basically restore the symmetry. So there's a region below 10 GeV, which is excluded on theoretical grounds. But as I'll explain to you, the region below 114 GeV is excluded experimentally. So if the standard model is literally correct, the Higgs must be greater than 114 GeV. And there's another constraint that comes from precision electroweak. Basically, if you look at diagrams with the Z and W, there are diagrams like this, where this vertex is actually the vertex by which the Higgs gives the Z mass, right? There's a coupling V squared Z squared, which is exactly the mass term for the Z boson. But if there's a V, I can always make that V plus H. And then I can look at the term linear in H. That gives rise to a vertex between two V's and a physical Higgs boson. If that vertex exists, I can draw this diagram. If the Higgs has infinite mass, this diagram is quadratic, is divergent. And when you put that all together, what you find is that there are effects. Actually, the quadratic divergences cancel when you look at observable quantities. But there are effects that are alpha weak over 4 pi times the log of the Higgs mass divided by the Z mass that correct the predictions of the standard model for these precision electroweak quantities that I discussed on Tuesday. And because the precision electroweak theory works basically perfectly, these things must be extremely small. And so that puts a limit on the Higgs mass, and that limit is quite strong. It's about 180 GeV up here. So if the standard model is correct, then the Higgs lies, and we haven't discovered the Higgs yet, which we haven't, then the Higgs lies in this relatively narrow region between 114 and 180 GeV. And so now let's just talk a little about what the Higgs should look like experimentally, and then we'll talk a little about the quest to find this particle. So the next thing we ought to do is to work out the pattern of Higgs decays. What does the Higgs decay to? And to do that, I'd just like to extend the analysis that I did here. Basically, everything that gets mass from the Higgs boson is also a potential decay product, because every time in the previous lecture I had a formula with a V in it, I can just write V goes to V plus H, and then if I pick up the term linear in H, I get a coupling of the Higgs particle to whatever it was that got mass. So, for example, if I have any fermion in the theory, I get here the mass of the fermion divided by V as the strength of this coupling. And I've already, I hope, convinced you in Wednesday's lecture that these couplings are all scalar couplings, and they conserve flavor. And that happens not because I started it out that way, but because there's a change of variables in the standard model that I can use to make those couplings as simple as possible. And that's, by the way, the same change of variables that diagonalizes the mass matrix for the quarks and leptons in the standard model. Similarly, if I have W and Z, then I'm going to get here mw squared or mz squared divided by V. This comes in squared, so there's a factor of 2, and a g mu nu, they're vector particles. Here there's a 1 in the Dirac indices. And so, and please notice that this is of order G. This is of order the Yukawa coupling. This is of order G. And even the Higgs itself has a coupling like this. This came out of a 5/4 term, so a 3 appears here. So, OK, well, those are the Feynman rules. So now we can just start computing. So the first thing that you might say is, well, if the Higgs is heavy enough, it can decay to W's and Z's. And that should be something we can just compute the rates for that by taking this vertex, and you square it, and you sum over polarization states. And so that's a very straightforward exercise that I recommend to you. I'll write down the formula for W's. The formula for Z's is very similar. So the first thing you should expect is an alpha weak over something times mh. The thing you might not expect is that mh over mw to the q squared appears here in addition. And then there's some more detailed factors that, if you're interested in this, you should try and derive. This is mw over mh now. And then this is phase space, 4mw squared over mh. So this factor here is a little surprising. What it says is that as the Higgs gets heavy, this decay rate actually increases dramatically. When the Higgs is of order 700 GeV in mass, the width of the Higgs is equal to the mass of the Higgs. And the Higgs becomes a huge, broad resonance that kind of disappears, a resonance in WW and ZZ scattering. And, but frankly, that's not surprising, because this factor here is just the factor that turns alpha weak into lambda over 4 pi. And if you think about the Higgs, before we turned on the electroweak interactions, it actually has a coupling to the Goldstone bosons of the, which are other components of its multiplet that were then eaten by the W bosons. And so this interaction has strength lambda. After the Higgs mechanism acts and the W bosons get mass, that interaction's still there. So there has to be some very strong decay of the Higgs if lambda is large. The interpretation is that the phi plus and phi minus become the longitudinal components of the W plus and W minus. And indeed, if you go compute this by computing all the helicity amplitudes, what you find is that the dominant term occurs for 2 longitudinally polarized W plus and W So this is a rate that becomes very large. When the Higgs mass is large, it's actually always large. Whenever it is available, it's the dominant mode of Higgs decay. Okay, so maybe it's not available. Maybe the mass of the Higgs is less than 2mw. And maybe I should just say there's a similar formula for the Z with half the coefficient here. That's a weak isospin relation. Okay. When the W is not available, the Higgs might want to turn into fermions. And here the formula, there's always an alpha weak and m Higgs. Here, the fermion mass must come in. So there's an mf over m Higgs squared that comes here, and a 1 minus 4 mf squared over mh squared, I think to the 3/2. And if it's a quark, the number of colors appears here, so you get a factor of 3. mf over mh is typically a very small number. Of course, not for the top quark, but if the Higgs can't decay to the W, it can't decay to the top quark either. The next choice is B. For B, this is 5 GeV. So now we're talking about 5% squared. So we're talking about a 10 to the minus 3 coming from this factor. And so all of a sudden, when you go below the W threshold, the Higgs gets extremely narrow, and its decays are very restricted. Now, actually, this makes the Higgs a little more interesting, because if the leading decay is very restricted, that means that other subdominant decays can also come into play. And so let me tell you a couple of them. One is that the Higgs to WW can still be around. It's just you have to let one of the W's go off shell in order to conserve energy and momentum. So then you get a higher order process where, for example, one W is real and has its usual on-shell decay, and the other W is off-shell, and then it goes on-shell when it decays to lepton neutrino or to QQ bar. And as I say, because this number here is a suppression of 10 to the minus 3, and this is order alpha, there's plenty of room for this kind of diagram to play in as well. Another thing that can happen is that you can have higher order processes. And so a very fascinating process, once again, if those of you who are interested in standard model phenomenology, you should do these calculations. It's quite an interesting thing, is that the Higgs can couple to some quark, and the quark can then exist virtually and decay to gluons. Now, let's think about this diagram for a moment. There's an integral d4k. There are 1, 2, 3 quark propagators. So there's a k cubed. And maybe I should say what do we want to say here? There's always a trace with which involves the mass of the quark. And then the thing can't be completely helicity conserving. Oh, no, I'm giving the wrong argument. I'm sorry, I'm really giving the wrong argument. So if I look at this vertex, it involves 2 gluons and a Higgs field. So let me try and write a gauge invariant effective Lagrangian that this would come from. And so that gauge invariant effective Lagrangian would be something like f mu nu squared, because I need to write a gauge invariant operator that produces 2 gluons, and it has to have a Higgs field. So when the smoke clears, there has to be a dimensionful factor out in front in the effective Lagrangian And so when you compute this integral, it has to be finite. Now, typically you would say the integral involves a factor of mf. But from the denominator, you actually get a factor of 1 over mf or m Higgs, whichever is larger. So, and then you get a factor of 1 over v in the Higgs. This is mf over v in the Higgs coupling. Now, if the Higgs is heavier than the quark mass, a large momentum flows through, and that dominates the loop integrals. If the quark is very heavy, it's the factor mf that dominates. So something very weird here happens. If the quark is light, we get mf over m Higgs, which is negligible. If the quark is heavy, we get mf over mf, and the quark mass cancels out. So the only quarks that contribute to this diagram are the ones that cannot occur in Higgs decay. And oddly, in the standard model, what happens with this constraint on the Higgs mass, the only thing that contributes is the top quark. And the rate is alpha w, alpha s squared. There's an m Higgs cubed over mw squared. That's your factor of 1 over v squared. And then a somewhat small coefficient appears, 288 pi squared, I think. So it's interesting. It's a number here which is of order 1 for the Higgs below the W threshold. It's suppressed by 2 powers of alpha s and a large factor. But nevertheless, because it's competing with this 10 to the minus 3 here, it's not an insignificant decay mode. For a Higgs of, let's say, 120 GeV, just above the current limits, basically the dominant decay is BB bar. This thing corresponds to a 15% branching ratio. And this is about a 5% branching ratio. And maybe I should just say you can do the same thing with photons. So with photons, you can have the Higgs decay through the top quark loop, or also there's a decay through a W loop. And these things give you a similar formula with an alpha here, so it's somewhat smaller. So in this case, the branching ratio is 2 times 10 to the minus 3. So once again, for an m Higgs of 120, this thing is the dominant decay. This guy here is 15%. This guy over here is about 5%. There's another 5% which goes to tau plus tau minus. This guy here is a 10 to the minus 3 decay. And so if you kind of put all these things together, you can get a complete picture of the Z branching ratio, of the Higgs branching ratios. And it's actually kind of a complicated story. If you go to the slides now, what you see are 3 pictures of the Higgs branching ratios for 3 different regimes of the Higgs mass. So in the first of them, you see the regime below. So this is on a log scale going from 10 to the minus 3 up to 1. The first one is the regime when the Higgs cannot decay into on-shell W and Z. So you see the dominant BB bar process, and then all these subdominant processes appearing at the percent level. Tau tau, glue glue, charm anti-charm, gamma gamma, etc. On the next page, you see what happens when you go through the vector boson thresholds. All of a sudden, WW becomes absolutely the dominant process. Then you go through the Z threshold, and that kicks in. And then it's going 2 to 1 into WW and ZZ. And everything else goes away. And when this actually comes in, the BB bar, instead of being dominant, becomes a 10 to the minus 3 branching ratio. Although to test the theory, you might actually want to observe that. It's an interesting experimental challenge. If you now turn the page, you see what happens at the top quark threshold. The top never quite gets as large as the W's, because the top is only coming with the top Yukawa coupling, whereas the W's, as I've said, are coming with the Higgs coupling, which is actually very large for a Higgs that's that heavy. And so now what you can do is to try and look for the Higgs in various channels. And so I think I'll make this story very brief because time is running out, but there's more about it in the notes. So you can look for the Higgs at various places, and then you can get some experimental constraints. The strongest existing constraints, actually, right now, mainly come from LEP, from E plus E minus annihilation, from the following reaction, where you have electron-positron. You make a virtual Z, which can then go on shell as a real Z, giving off a Higgs boson, that you then observe in its dominant mode of BB bar. So then you would have BB bar plus whatever the Z decays into, L plus L minus, an invisible decay to nu bar, producing only the BB bar in the event, or QQ bar. And in the slides, I actually give some, essentially the mass distribution of the BB bar system from the very last data taken at the LEP collider, which went all the way up to 208 GeV. There's a reaction E plus E minus to ZZ, where Z goes to BB bar, which is very clearly observed. That's the big peak in those diagrams. And there's just a tiny hint that there might be something beyond that peak. But let's just say such tiny hints often occur in the last days of accelerators, and it never became statistically significant. So all one could really do is to put a limit, and that's where this number that M Higgs is greater than 114 GeV comes from. Well, right now, you know, at the Fermilab Tevatron, people are trying very hard to find the Higgs. And there are basically two ways to do it. One is to look at the analog of this process, where you have QQ bar, let's say going to W and Higgs or Z and Higgs, looking for this in BB bar. The other way is to do the inverse of the glue-glue decay. So you have glue-glue to Higgs. Then you can look at this in a WW star final state. If both W's decay to leptons, then you get two opposite sign leptons, missing energy, and nothing else in the event. It's a very clean signature. And so this actually seems to work. They've excluded, unfortunately they haven't found the Higgs, but they've excluded a region around 160 GeV. So remember I told you that there's a bound of 180 that comes from precision electroweak, but there's a region near the top of that range which is excluded by the non-observation of this decay. And here I think there's still a way to go to get significance above the number of 114. And then, yes?
I know this isn't the sole purpose of the LHC, but if the Higgs mass is going to be less than 180 GeV, why does the LHC go up to 14 TeV?
Oh, because when well, A, it's not the sole purpose of the LHC, and you're right about that. Secondly, when I discussed the precision electroweak, that statement is really applies just in the very narrow context of the standard model. So if you say, well, there's a radiative correction that shifts the properties of the Z and W around, and that shift is not compatible with experiment, I can always fix that by adding another radiative correction, some new heavy particles that have the opposite effect. And actually, about 10 years ago, I actually wrote a paper that cataloged all the ways you could do that. It always involves new particles. And there are some definite kinds of new particle properties that can fool you into just shifting back the prediction of a heavy Higgs. So if you don't take that so seriously, and I guess I encourage you to think that there might be a possibility that the Higgs might be heavier, 200 GeV, 300, etc., then you might need more dynamic range. Eventually, I think you'd like to measure WW scattering at 1 TeV anyway, just to see that maybe there's some reason why that couples to some new strong interaction sector, or maybe that's involved in this. For that, you really need the full power of 14 TeV and maybe even higher eventually. So I think really if you want to explore the TeV region of masses, you need this very high energy accelerator. Yes?
If the protons are at 7 TeV each, what are the partons actually interacting at? I mean, that's
Oh, well, I think, so the typical parton interactions are, 1/10 to 1/20 of that. But there are some partons that are, at a third, a fifth, something like this. So if you ask a question like, if there's a new kind of quark, up to what mass can I discover it at the LHC? The answer is about 3 TeV. So that would correspond to 6 TeV in the center of mass from a 14 TeV proton-proton initial state. And in principle, there are events that occur even higher up. It's just you run out of steam because these parton distribution functions go to 0 when x goes to 1. So, it's an exploration. You want to go to the limits of your technology. So then finally, at the LHC, there are multiple ways to look for the Higgs boson. As we've already said, you have plenty of energy to find the Higgs in WW and ZZ if it's energetic enough. ZZ goes, by the way, to 4 leptons. So this is a very dramatic signature. And if you find all 4 leptons and you add up their momentum vectors and there's a peak, you can't beat that. Here, you can look for this kind of signature. And you can try from the distribution of the leptons to reconstruct, at least make some kind of likelihood curve for what the mass of the Higgs should be. For the light Higgs, the mode which is most considered is actually Higgs to BB bar is very discouraging. Because what it is a bottom-antibottom pair that you're producing in proton-proton collisions. Of course, there are a million other ways to produce bottom-antibottom pairs, like 2 gluons come together and they just make bottom quarks. This process has a cross-section about 1,000,000 times larger than that cross-section. So that's a very discouraging prospect. Recently, there's been some interest in whether you could see the process of QQ bar to W or Z plus Higgs, where the Higgs goes to BB bar and where the Higgs is highly boosted. And there have been some interesting investigations recently that a boosted Higgs, basically the boosted Higgs looks like a single jet because the pieces are all going in the same direction. And there's some tests for whether that jet is a normal QCD jet or an exotic jet. And it's thought that maybe with those kinds of analyses you could get sensitivity to this process. And then the other way is to look for glue to Higgs going to gamma-gamma. And you probably noticed that both of the LHC detectors, and in particular CMS, has a very sophisticated technology for measuring the energies of gammas. And that's more or less specifically devoted to being able to find a resonance in gamma-gamma in this decay and find the Higgs in that way. So I'm sorry, you had a question. You had a question? You had a question. Sorry? Well, we talked about jets. So the jets come from this parton shower process. So the parton shower process it's very well characterized. I wrote all the equations, or you even worked out some of the equations for it. So, so we know kind of what this bundle of particles looks like that makes up a typical jet that, let's say, originates from a gluon. So you might test and see whether a jet that you actually observe has those properties. So if you have a gluon jet, then remember these splitting functions typically go like 1 over z. So every branching, there's a fast guy and a slow, and a hard guy and a soft guy. But when a heavy particle decays into two equal mass things, it decays equally. So the first thing is equal splitting. So if you can actually kind of carve back the jet to its original components and see whether it had unequal or equal splitting, then maybe you could tell this from this. And in the simulations, it seems to work. Whether it'll work in experiment, we'll find out. Okay? All ideas that you might have would be appreciated, because it would be really nice to find the Higgs boson. Yes?
The energy ranges that we're looking for Higgs, to what extent do those depend on the assumption that there's only one Higgs? So we've cleared out regions where it could possibly still exist in, right?
Right. Everything I've said is literally, all that is there is the standard model. Okay, as soon as you go beyond the standard model, everything opens up. The Higgs can easily go to 200 or 300 GeV, in which case, by the way, it would be really easy to find through this mechanism. You guys did this tutorial yesterday where you showed that if there are 2 Higgs fields, then there are actually 4 more particles. And those could be very heavy. And they can have their own characteristic decays. Like there could be a charged one that decays to TB bar. That would really be fun to find. Okay. So once you go beyond the standard model, everything opens up. Okay. So maybe this is the time to come to the end. So before we come to the end, there's one more thing that I wanted to tell you, which is that in this course, I've been very rigorous with myself in only telling you things that are properties of the standard model, because that's my assignment in the school. I'm supposed to tell you about the standard model. So now the question is, do I think the standard model is correct? And the answer is no. And the reason is the things that I was hedging about at the beginning of the lecture when you guys were asking me about the Higgs potential. Because I really do want to emphasize to you, I think that this model where you say you introduce one scalar field and you write down a potential for it and you put a minus sign in front of the quadratic term, and that's the explanation for spontaneous symmetry breaking in nature, it just really doesn't make any sense to me at all. It's perfectly mathematically correct, and it could be true, but it has some serious problems. I mean, first of all, the question is, why do you put that sign there? There's no explanation for that. It's a postulate of the model. And it's not the kind of thing that you would postulate in physics. In physics, you would want to postulate a physical explanation. But if you start computing the radiative corrections within this model, it gets even worse. This term gets radiative corrections from 3 kinds of things, actually lots of things, but there are 3 very important one-loop radiative corrections from the Higgs self-coupling, from the top, and from the W. And if you compute those corrections, they're all quadratically divergent. This one goes like lambda over 4 pi squared times whatever cutoff you put on the theory. This one, lambda t squared. And this one, alpha weak. And these 2 are positive, and this one is negative. So it's not entirely clear whether the correction to the theory is clearly out of control. It depends on whatever cutoff you put on the theory, which means it depends on some new physics which is outside the standard model. And in fact, the sign of the correction is not clear. If there's a somewhat different cutoff for these modes, then it might be this one that dominates, or this one, or this one. And so the statement is not that the original mu here is negative. The statement that mu renormalized, which is equal to the mu bare, whatever was the original parameter, plus the radiative correction, is less than 0. And this thing is a number that's out of control. And this thing is something that we don't even know what the sign is. So I believe it is impossible within this model to predict that SU2 cross U1 is spontaneously broken. And in order to solve that problem, you have to go to a bigger model where SU2 cross, where there's some way to calculate this potential from some more deep principles. But what that means is that you need new ingredients, new particles, new forces. We really need to find them. The energy scale of this potential, we know perfectly well what it is. It's this number of 250 GeV, which means that whatever creates the potential, if there's actually a physics explanation for it, should have effects at the 100 GeV, few hundred GeV mass scale. So there should be new particles and forces at the few hundred GeV mass scale. And, well, we've got this LHC. It's going to go all the way up to 14 TeV. We're going to find them. That's going to happen, I think, within your era. And those of you who were, well, so, you know, I could be right or I could be wrong. If I'm wrong, the LHC will discover this Higgs boson. It'll have all the properties that I suggested in this lecture. Particle physics will be over. And there won't be anything new to discover except maybe at the scale lambda, which might be, you know, at 10 to the 14, 10 to the 16, maybe not until the Planck scale. And we might never be able to get there with an accelerator. On the other hand, if I'm right, then even this year we could start discovering new particles of mass 200 or 300 GeV that are relevant to this story, and a whole new era will open in particle physics. So I sure hope I'm right, and you guys hope even more, because if I'm right, your lives are going to be very exciting. And I wish you the best with it. So that's the end of the course.